going to talk about. Okay. Hi guys, today's lecture is going to be about showing quantum state. This lecture was mostly developed by Solgat Kumar and I, Emilio Peláez, will be presenting it to you. So the things that we're going to cover in this lecture are the no-cloning theorem, which is a principle of quantum mechanics that we're going to apply to quantum computing. Then quantum teleportation, superdense coding, and quantum key distribution, which all three are protocols of quantum computing, protocols or circuits. So they are like real applications of quantum computing. So let's start off with the no-cloning theorem. This theorem says that it is impossible to create a copy of an arbitrary quantum state. In other words, there is no unitary circuit U such that performs the operation in equation 1. So this is just an arbitrary quantum state. So it's alpha 0 plus beta 1. And T can just be any state. So there is no unitary that takes the state on the left to the state on the right, which is two copies of the state psi. So this theorem says that there is no unitary that can do this for any quantum state. So any combination of A and B, well, alpha and beta, sorry, obviously with the condition that they are normalized so that they are real quantum states. But we know that in classical information, we can easily copy a bit. There is the fan-out gate that gives us two copies of a simple bit. So there must be some type of restriction of quantum states that allows us to create some unitary that allows to copy, not clone, but copy some type of quantum states. So we can figure this restriction first by assuming that something like equation 1 is possible. So this is like just like in equation 1, we have one state that is copied into 2. And in the next equation, we also have another state that is copied into 2, okay? So now to get a relationship between psi and phi, we can take the inner product of equations 2 and 3. So the left-hand side will just look, we will leave equation 3 as it is and take the complex conjugate of equation 2. So let's just do it. This is the side of equation 3, and this is the side of equation 2. And we just use, remember that all the gates are unitary, so the complex conjugate of a unitary is the same as the inverse. So the condition for a gate to be unitary is that U times U dagger equals the identity. So in the next step, as you can see, we can just get rid of U dagger times U. So that's what's happening there. And on the right-hand side, we just take the complex conjugate of the right-hand side of equations 2 and 3. So this is from equation 3, sorry. And this is from equation 2, okay? So in the next step, we just get rid of the U and the U dagger. So just like I explained, this is a condition of unitary gates. And then we can simply distribute. Just to remember that the tensor product, we can get rid of it just to make it more readable. So let's write this equation here again without the tensor product. Phi t equals psi, phi, and phi. And just moving around these things, we can do it. This with this one, this with this one, and that's equation 6. And the same in the other side, we get this with this one, this with this one. And here we have the inner product of a vector with itself. And the inner product of a vector with itself will just be its magnitude. And since these are all valid quantum states, the magnitude of the get t is just 1. So this is just equal to 1. And that's how we get rid of it on equation 7. And in equation 7, we're just left with this times the same squared. So we need to, this is the relation between the state phi and the state psi, such that there can exist some unitary as in equation 1. So such that there exists a unitary that can clone the states. And the only values that are able to satisfy this condition are 0 or 1. So let's see what this means. So if the inner product is equal to 1, as I said in the previous slide, with how we got rid of the inner product of T with itself, this just means that the state sorry about that, the state psi and phi are the same. So that says that we can create a unitary that is just able to clone one specific state. And then if we have psi and phi equal 0, that means that psi and phi are orthogonal. That's just a property. We can just check it with 1 and 0 and 0, 1. So let's take the inner product of that. We get 0 times 1 plus 1 times 0 equals 0. And we know that they are orthogonal because they sit like this in the axis. And they have a 90-degree angle, so they are orthogonal. So yeah, there exist two types of unitary gates that can copy some state. The first one is that it can just copy one specific state, which isn't very interesting. And the second one is that it can copy two different states such that they are orthogonal. So this is very simple to see with the CNAT gate, because it is able to clone either the 0 or the 1 state, which are orthogonal, just using a 0 qubit as the ancilla. So this is the one we want to copy in both in equations 8 and 9, and applying the CNOT to the 0, 0, we get again 0, 0. So now we have two copies of the 0 state, which we wanted to clone. And then the same with the 1 state, it applied to 1, 0, we just get 1, 1, which gives us two copies of the 1 state which we wanted to copy. So now let's try it for an arbitrary state. We put the arbitrary state that we wanted to copy as the control, and we put the 0 bit again as an ancilla qubit, an extra qubit. So what we get is the entangled state, that this is just a Bell state, is the circuit that we made you do as bonus in problem set 1 and yesterday in problem set 2. So it may look like this is the state we wanted to copy twice, but this is not true, because if the state was cloned, it would look something like this. So tensor product with itself. And remember that the tensor product is very similar to normal multiplication. So A times A, alpha squared, 0, 0, plus alpha times beta, 0, 1, then beta times alpha, 1, 0, plus beta squared, which is just this, 1, 1. And as you can see, this is not equal to what we got on equation 10. So the state is not cloned. The CNOT gate is not able to clone an arbitrary state, just the 0 and 1 state, which are orthogonal. So yeah, that's basically the non-cloning theorem. Are there any questions about this to this point? Min, are there any questions?
Let me check the chat real quick. Give me a question.
Yeah.
So go back a few slides.
Here.
One more slide. Oh, wait, that slide. Yep.
Yep.
Go back. Go forward one. Oh yeah. Okay. So this is good. Can you like explain a little bit again by what do you mean that you can only clone orthogonal states and not like exactly the same state?
Okay. Yeah. So from this slide, we assumed that equation 1 is possible, that there is a unitary that is able to clone some state, okay, some arbitrary state. And we got equations 2 and 3 that just resemble cloning two different states, psi in equation 2 and phi in equation 3, okay? Then to get a relation between psi and phi, we took the inner product of equations 2 and 3. So that in equation 7, we got that the inner product of psi with phi needs to be the same as squared. And the only values that satisfy that are 0 and 1. So having an inner product of 0 means that the states are orthogonal, and having an inner product of 1 means that they are the same. We're just focusing on the case in which it's the inner product is 0. So that's basically why we can only copy orthogonal states, because that's the condition that makes such a unitary exist. And you can see it right here, because we were able to copy these two states. So we're able to copy 0 and 1, which are orthogonal, because look at the lower right, upper right side, taking the inner product of 1 with 0, we have again 0 times 1 plus 1 times 0 equals 0, which means they're orthogonal. And graphing them, you can also see that, because let's take this to be 1, 0, and 0, 1. This is just the normal coordinate system, x times y. And you can see that they form a 90-degree angle. So that's, there you can see that they are orthogonal. And when we tried it with an arbitrary state, which just means that some alpha value for 0 and some beta value for 1, we saw in equation 10 that we do not get 2 copies of the quantum state. We got this. That is just the Bell state. And the Bell state is not equal to the two copies of the arbitrary quantum states. It should be equal to this if it was able to clone it, but it isn't able to clone. So yeah, that's it. Any other question?
I think you're good for now. Continue.
Okay. So with the no-cloning theorem, we can now start with quantum teleportation. So we cannot send a copy of our state. We cannot copy it because of the no-cloning theorem, but we can send the state itself, the information that the state contains, by exploiting quantum entanglement. So suppose Alice has some quantum state, which we will call psi sufindex C, which the sufindices will just help us like identify the qubit to whom it belongs. So qubits C and A are from Alice, and qubit V is, I'll just write them out, is from Bob, okay? So yeah, so the state that Alice wants to send to Bob is an arbitrary quantum state. It's just some value of A alpha plus some value of B, so it's this one. And then each of them has one qubit from an entangled pair, okay? So before Alice even knew which state she wanted to send to Bob, they were together, they made a Bell state and they took one qubit with each other. And this is an important thing because you have to remember that entangled pairs affect each other no matter the distance. So if at some point you entangle them and then don't apply any more unitary, you assume that they do not interact with the environment, they are not disturbed. If you take them as far away as you can, the states will still be entangled. So this is important because this is an entangled pair, but qubit A and B are not together, okay? Like not physically together physically. So the circuit that is going to allow us to teleport the state C to the qubit B that Bob has is this one, where we will go through it just right now. Just let's analyze the circuit. So as I said, this is from Alice, this is from Alice, and this is from Bob. And between this one, these two wires, these two qubits, there can be any distance, okay? And here we're already, like the input to this state is already the state we want to send in the top qubit, in qubit C, and in qubits A and B, we already have the entangled state, so we do not have to prepare it, it was prepared beforehand. So yeah, the initial state is just the tensor product of psi C with the psi A and B, which is just the Bell state. So yeah, this is just taking the tensor product to get the overall state. So it's just like 0 times 0, 0. We get this one, then again 0 times 1, 1. We get this one, then with beta 1 times 0, 0, 1, 0, 0, again 1 times 1, 1, 1, 1, 1. So this is just like getting the overall state of the whole system, so we can work with it all together. So now we apply the CNOT gate with the controller C and the target C, which that's what these indices denote. The first index is the control always, and the second index is the target. That's the same as here, the control and the target. So yeah, we're going to look for the states in which the control qubit C, is in 1. So it's just this one and this one. So that's in those states, those elements of the superposition, we're gonna flip the qubit A. So that's what we do here. This transforms to this with this flipped, and the same, this transforms to this, qubit A flipped. So that's how we apply the CNOT gate, and we got that state. And let me just write this down like more condensedly. Remember that we can just put everything into a single ket just to make it easier to work with. So this will be alpha 0, 0, 0. And this just preserves the same ordering. So qubit C, qubit A, qubit B. Times beta 1, 1, 0 plus alpha 0, 1, 1 plus beta 1, 0, 1. So let me copy this. So now we're going to apply an edge gate, a Hadamard gate on the qubit C, which is, remember, it's the first one. So we're going to apply it on those qubits. And just remember that the Hadamard gate on the 0 state takes it to the superposition of 0 plus 1 without any negative phase. And on the 1 state, it takes it again to the superposition, but with some negative phase on the 1 state, okay? So now what we simply do is first, we note that in every element of the superposition, we're gonna get a factor of 1 over the square root of 2. So we can just get rid of that right away, take it outside the parentheses, sorry, and that multiplied by the other 1 over the square root of 2 that we had earlier just gives us 1 over 2. So now we don't need to worry about normalizing. So yeah, so first with the first element, we have 0. So it turns into 0 plus 1 without any negative phase. In the second state, we have 1, this one. So 0 minus 1. Then again 0, so 0 plus 1. And then we got another 1, so 0 minus 1. Okay, so that's the superposition, which we can simplify to the next state you can see. And this is like a bit of lengthy, so let me just do it in the next one. So again, we just write it condensedly. So we do alpha 0. We write it condensedly and then we expand the parentheses. So it's just like a normal multiplication. So this times this, then this times this. So 0, 0, 0 plus alpha 1, 0, 0. And we do this for every parenthesis. Beta 0, 1, 0 minus beta 1, 1, 0 plus alpha 0, 1, 1 plus alpha 1, 1, 1 plus beta 0, 0, 1 minus beta 1, 0, 1. Okay. So in this state, we see that we want to get the common factor, sorry, of qubits C and A. So this works just in normal multiplication. We will get common factors of the first 2 qubits. So here we see 0, 0, and we also see it here, then 1, 0, and we also see it here, then 0, 1, and we also see it here, and then 1, 1, we also see it here. So we can just take this out to see if it is a common factor in normal algebra expressions. So again, 1/2, and we get, let me just do it in purple, 0, 0. And the first one with the alpha, the remaining is 0, alpha 0, and then beta 1. Then let's do 0, 1. And that's alpha 1 plus beta 0. Then we have 1, 0, which we got alpha 0 minus beta 1. And finally, we have 1, 1, which is just alpha 1 minus beta 0. So we just took out the first two qubits, like in which we had common factors, and just did move the right side. So let's just take the, so yeah, this is basically the state where we end up with, which is the same this one, just we simplify it from the top expression. So yeah, now we're on up until here on the quantum circuit, we're up to the state where the red line is. So we only have measurement left. And as you can see, after measurement, we still apply some gates to qubit B, which is this one. And these are represented by x to the m2 power. So let me just write that down, x to the m2. So this just means that if the measurement in this qubit is 1, we apply it. And if it's 0, we don't do anything. So just like in normal algebra, if x is to the 0, just any number to the 0 is 1. With matrices, any matrix to the 0 is the identity. So it's like no matrix is applied. And if the measurement is 1, it's simply, it's simply the normal gate. And the same with the measurement of the top qubit with M1, okay? So yeah, the possible measurements just are summarized in this table. So let me just get this one so we can look at it. Okay, so remember that the first two qubits are qubits C and A, like from top to bottom, they're qubit C and A. And qubit C corresponds to M1 and qubit A to M2. So yeah. So if we have M1 and M2, which means that qubit 1 and qubit 2 are 0, we just have the purple one. So it's this one because that's the state we measure in the first two qubits. So all the other elements of the superposition disappear because we already know that the first two qubits are in those states. So we have that the state in qubit C, in qubit B is already the state we wanted to teleport. So the teleportation is complete, okay? So now let's look at what happens when M1 is 0, but M2 is 1. So in this case, we will have 0, 1. So it is the red state, this one. And that corresponds to the state A1 plus B0, which is just the same as an X applied to the qubit P we wanted to teleport, okay? So just X, B, remember that this was alpha 0 plus beta 1. We just flip 0 with 1, 1 with 0. So it's beta 1 plus alpha 0. Sorry, I did it wrong. It's alpha 1 plus beta 0. And that's actually the state we measure when the first two qubits are 0, 1. You can see it here. And then it's the same thing with this one. With this state, we're going to measure alpha 0 minus beta 1, which is just applying a negative phase to the 1 ket in the normal state we wanted to teleport. And that's the action of the C gate, so that's all right. And then this one is this state, which is just A ket 1 minus beta, so alpha ket 1 minus beta ket 0, which is just a C gate and then an X gate. So yeah. So as you can see in the three lower cases, we do not have the state we wanted to teleport right away. We have to apply some corrective gate. And this corrective gate is given by these two. These two are the corrective gates that depend on the measurement. So as you can see, if we have 0, 0, we just don't apply anything. And we apply these gates depending on the other measurements. So let's just do it. So as I said, we just apply that entity if we got 0, 0. So that entity doesn't do anything. So we're just gonna end up with 0 plus beta 1, which is already the state we wanted to send. So if we got 0 and 1, we apply an X gate plus beta 1. Sorry. We apply an X gate to the state we measured, which is alpha 1 plus beta 0, which we just flip, and we got the state we wanted to teleport. Then with the measurement 1, 0, we apply C gate to the state we measured, that is alpha 0 minus beta 1. And then remember that the C gate just applies a negative phase to the ket 1 and does nothing to the ket 0. So this just states it's beta 1. And as you can see, this is also the state we want to teleport. And for the final, we apply Cx. And remember that here we're going to write Cx because we're doing it like the matrix multiplication. And in this, we have x and then c. But this is just like the same thing because this goes from left to right. So it applies first x and first c. And matrix multiplication just goes from right to left. So again, we apply first the x and then the c. So it's the same thing. So yeah, we're going to apply Cx to alpha 1 minus beta 0. So first applying the x gate and leaving the c, we flip. So alpha 0 minus beta 1. And then just applying a negative phase to ket 1, we got alpha 0 plus beta 1. As you can see, that's the state we wanted to teleport. And in all cases, the state we wanted to teleport goes from qubit C to qubit B. So that's basically how we teleport the state. And although the state was sent from qubit C to qubit B, we did not violate the no-cloning theorem. And this is because of the measurement. So in the measurement, the state of Alice of qubit C collapses. And therefore, there at any point, known point in the protocol, we have two copies of the state psi. So we did not violate the no cloning theorem because we didn't have two copies of the same state at any point in the protocol. And it is called teleportation since physical qubits were not exchanged between Alice and Bob, just the entangled pair, but that was done like before the protocol. That is not part of the protocol itself, and only classical information was exchanged. And the classical information was the one in these wires that actually needs to be sent by optical fiber or any other type of classical communication that we use today. Okay, so that's basically the quantum teleportation protocol. Are there any questions about it?
Yeah, can you go through again the corrective phase after the measurement? Just go through it again. But
okay, so we need the corrective gates because we have these possible states, okay? The ones noted here. So remember that the state to send is psi, which is just, again, an arbitrary state, alpha 0 plus beta 1, okay? So that's what we want to measure, to have in qubit B. So if we measure 0, 0, that collapses the state to the one in purple. So that's 0, 0, alpha 0 plus B1. Okay, so in that case, we already have, this is already psi. That's what we wanted to send. But take a look at when we measure 0, 1. So when we measure 0, 1, all the three other elements just disappear, and we collapse to the wave function with 0, 1 on the first two qubits, and we got A1 plus B0. And here, we do not have the state we wanted to send. This is not equal to psi. But applying an X gate to this will simply give us the state psi that we wanted. And the same with the other ones. When we measure 1, 0, we just have a negative phase on the ket 1, which can be corrected by a C gate. And when we measure 1, 1, we just have a negative phase first applied to the ket 1, and then we flip the kets, and we can just correct that by doing the inverse operation, that is first flipping and then applying the negative phase. So that's why we need corrective gates, because not every time we get the actual state we wanted, but we can correct for that with the measurements. And if we didn't need the corrective gate, we would get rid of like all of this. So there will be no measurement. And if there is no measurement, the state in qubit C does not collapse. And if the state on qubit C does not collapse, we have two copies of the same state. So the no cloning theorem is violated. So that just can happen because of physical laws. I think there are more questions here. In teleportation, we still use fiber, which connect Pablo and Alice, right? So it's teleportation, the same speed as classical one. Yes, so in teleportation, with the two, with these two classical channels, we will send them through classical channels. So just the speed of this protocol depends on the speed in which we can send classical information through. And this also is really nice because that way we do not violate that information cannot travel faster than light, because we still rely on classical information that cannot be sent at a speed faster than light. So that's really nice. Are there any more questions in Discord or something? Well, if not, I'm just gonna carry on. So now superdense coding. Superdense coding is a quantum communication protocol that allows us to send 2 bits of classical information by now physically moving 1 bit. So it is a bit similar to the last one, but now we send 2 bits of classical information by physically moving just 1 qubit. So for this protocol, it is important to remember that when you apply a gate to 1 qubit from an entangled pair, the other qubit will be affected no matter the physical distance between them. So this is just what I talked about in the last one when I said that qubits from Alice and Bob can be any distance apart. So this protocol, just like the last one, exploits this fact to encode classical information in a pair of entangled qubits. And superdense coding just applies gates to 1 qubit, but is able to communicate 2 bits of information. But just keep in mind that Alice is not encoding 2 bits of information into a single qubit because that's impossible. We're just taking advantage of the correlation of entangled pairs. So the complete circuit for superdense coding is the following, which, as you can see, is very similar to the last one. We just now have the corrective gates, which aren't corrective this time in the first qubit, and then we have the same C0 and H, and then we measure, okay? So the initial state we will send through the circuit. So this one is just the bell state, that is the equal superposition of 0, 0, and 1, 1. And the classical bit string, so the 2 classical bits is just B, which is B1 and B2, okay? So again, although the wires here seem to be physically together all the time, they can be as far as you want them to be during the encoding process. So here, far apart, but then for the decoding and the measurement, they need to be together because we are applying a CNOT gate, and the CNOT gate depends on locality. So the 2 gates, the 2 qubits to which we're going to apply the CNOT gate need to be physically close. So yeah, like in this part, we are gonna Alice sends qubit to Bob. So then Bob has both qubits for the decoding and measurement, okay? So again, we have X to the B2 and C to the B1, which is just an interpretation protocol. If B2 is 1, we apply the X gate. If it's 0, we just apply identity, so no X gate. And the same for the C gate with B1, okay? So let's just do this. So if the bit string is equal to 0, 0, we do not apply the X, we do not apply the C. So the final state is just superposition of 0, 0 plus 1, 1. So it's just the initial state again. So now we apply an X gate if the bit string is 0, 1. So B2 is equal 1, X to the B2 is X to the 1. So we just apply the X gate, 0, 0 plus 1, 1. And as I've sent to the Q&A channel on Discord, this is the same as doing X tensor product 1, which just means that we apply an X gate to the qubit on the left, so to the qubit on top in the circuit, and just an identity to the qubit below, which just is because we do not have any gates here, okay? So this just means flipping the first qubit. So we will have 1, 0 plus 0, 1. Then for the bit string 10, we got C, again, tensor product identity, 0, 0 plus 1, 1. We just apply a negative phase when the qubit on the left is 1. So that will be in the second element of the superposition. And that's it. And then we apply CX tensor product identity to the val state, which is just going to give us, let's just apply the X gate first. So we still have the C gate. For the X gate, we got 1, 0 plus 0, 1. And then with the C gate, we just get minus 10 plus 0, 1. Okay. So these are the states just before decoding and measurement. So these are the states that Alice will encode depending on the bit string she wants to send. And now we are up until the part where Alice will send physically the qubit to Bob. So she will send it. We're just going to suppose here that she will send them through an ideal quantum channel, meaning that there is no noise. So the state that Alice sends is the exact same that Bob will receive. And this is not quite true in reality, because when we physically move one qubit, it will very probably interact with its environment, which will alter the state. But let's just assume that we're working with ideal channels for this presentation, okay? So now the two final states, the coding and measurement, can be seen as one single step, which is measurement on the Bell basis, okay? So this can be thought of as the reverse encoding of the 4 Bell states, and the encoding of the 4 Bell state is what you did on the first problem of the Jupyter notebook of problem set 2. So encoding, just to remember, looks like 0, 0 goes to the Bell state we start with, 0, 1 goes to 0, 1 plus 10, 10 goes to 0, 0 minus 1, 1, and 1, 1 goes to 0, 1 minus 1, 10, minus 10, sorry. So the measurement on the Bell basis is just the opposite. So the arrows are reversed. Measurement is like this. So yeah, that's what these two do. So from here, it is simple to see the state we're going to measure. So measure, and using the values on the next slide, we have 0, 0 plus 1, 1. We simply get 0, 0, which is equation 13. So we get 0, 0, which is exactly the bit string we wanted to send, okay? So then again, measuring this one, which is 10 plus 0, 1, just corresponds to equation 14. So we get 0, 1, which is exactly the bit string we wanted to send. And then in the case number 3, we have 0, 0 minus 1, 1, which corresponds to equation 15. And then we just get, from measurement, you get 10, which is exactly the same as the bit string. And finally, the same for the last case, we have minus 10 plus 0, 1, equation 16, simply gives us 1, 1, which is exactly the bit string. So as you can see, this wasn't very complicated. It was really easy. We just altered the Bell state we had at the beginning to some other Bell state, and then we measured on the Bell basis to see what bit string gives that Bell state when preparing Bell states. So this state is pretty simple. Just as I said, we're assuming an ideal quantum channel, which is not actually true at the moment and will probably never be. There will always be some noise because quantum states are really fragile to the environment. They get altered very quickly, but this is just like something nicely theoretical that we can do assuming perfect quantum channels. So are there any questions about this? How many bits can be encoded in superdense coding? Only 2 classical bits? Yes. So we can only do 2 classical bits here because we depend on the Bell states, and the Bell states only are with 2 qubits. But we can extend this. So if we double the number of qubits, we could have like this, and then just the edge Hadamard gate, and the same here. So, and here again with the full basis. So we just like do the procedure twice, and we can send 4 bits of classical information with 2 qubits, and it scales like that. So 2 classical bits for each physically moving qubit, okay? Are there any more questions on Discord or something, Min? Okay, so if there are no more questions, I'm just going to go with quantum key distribution, the BB84 protocol. So in most cryptographic models, an encryption key needs to be shared between 2 parties. A problem with this is that these parties need to make sure that no one intercepts the key. If the key is intercepted, the security of the model and the information sent through it is compromised. So suppose that Alice and Bob want to make some bank transaction and they need to share a key to do this. So if some third party is able to intercept this key and knows this key, they will be able to get money from the bank account or something. So it is important that the keys are shared safely and only Alice and Bob know them, the 2 parties. Okay. So quantum computers can help us develop a secure channel to share this key, and BB84 is a quantum protocol that allows 2 users to share a key safely with each other. And one important thing is that with BB84, we just care about sharing the key. We do not care about what goes next. So it can be either a one-time path, an RCA protocol, so any cryptographic protocol that needs a shared key. Okay, so let's just get right off to it. So in this case, Alice will start off with 5 qubits that she can initialize to one of these states. So the normal 0 and 1 that we know, and the plus and minus, which are just, remember, just the superposition. And the minus state is just the same, but with a negative phase to the 1, to the ket 1. Okay, so the first 2 qubits, the first 2 possible states, form the rectangular basis, and the basis just means that the states are orthogonal, like we showed in quantum teleportations, 0, 1 are orthogonal, and the same is true for plus and minus, which make up the diagonal base. Okay, so we have 2 bases and 4 possible qubits, so 4 possible states or alpha qubits, sorry. So 2 states for each basis. So for each qubit, Alice would choose a basis and a bit 0 or 1. So if she chooses the rectangular basis and chooses bit 0, she will go with the 0 state. If she chooses the rectangular basis and the bit 1, she will go with the 1 state. And with the diagonal, 0 corresponds to plus and 1 corresponds to minus. So after initializing her qubits to some combination of these states, she will send them to Bob through an ideal quantum channel. So again, no noise. So once Bob receives the qubit, he randomly chooses a basis, rectangular or diagonal again, and measures it. After Bob finishes measuring, Alice and Bob share with each other the basis they chose. So they share, if Alice, let's say, she chose rectangular, diagonal, rectangular, and Bob chose diagonal, diagonal, rectangular, they're gonna share this with each other. Just that a string of bases, okay? So there are 2 possibilities. If Bob and Alice chose the same basis, they record the corresponding bit to the encryption key. So yeah, but if Bob and Alice chose different bases, they discard the corresponding bit. So in this case, just the first basis they chose is different, so they're just gonna discard that bit. So let's see why that happens. So let's say Alice chooses the R basis, then bit 0, so she will send qubit 0, okay? Then Bob gets it, and he has the chance, and he just out of good luck chooses again the rectangular basis. So since you're measuring in the same basis, you will get the same state. So this is when we keep the bit, because he will translate this to bit 0, which is exactly what Alice wanted to send. But now, if Alice again chooses the rectangular basis, bit 0, sends the get 0, but Bob now chooses the diagonal basis, he will have 50% chance of measuring plus and 50% chance of measuring minus, which is a 50% chance of getting the bit 1 and 50% chance of getting the bit 1. So this isn't useful because they need to be sure that the encryption key, that is the key they're sharing, is exactly the same thing. So if they have some uncertainty in the key, it will not work for the protocol. So that's why we need the measurements to be in the exact same basis. So they just got rid of the basis in which they do not chose the same one, okay? So let's just look at this. Again, Alice chooses the basis R, bit 0, qubit state 0. So Bob chooses the same basis, so he measures the exact same bit. Okay, so let's just assume that with their now sharing the basis. So we have, for the first qubit, we have R and R, so we keep that qubit. For the second one, we have R and D, so we get rid of this qubit because the bases are not the same. Now, from the second one, again, we do not have the same basis. Alice chose the diagonal one and Bob chose the rectangle one, so we can get rid of this one. And then for the last two qubits, they both chose the diagonal basis, so we can keep that. So as you can see, when they chose the same basis, they measure the same state and they get the same bits. So their final key is just the remaining bits. So it's just going to be 1, 0, 0, 1, 0. And this is the final key. And here we just got a 3-bit key, which will not be useful on real cryptographic protocols in RCA, one-time pad, or any other protocol. So this was just a small example, of course. In reality, this will be repeated hundreds and hundreds of times to get a 100-bit key, a 100 long bit key, or thousands of bits long. So yeah, this is just like a small example. In reality, this is done for a lot of bits. And just one more thing in here. So let's take a look at this qubit exactly. You can see that even though they did not choose the same basis, they both got like bit 0 and also bit 0. But there's no way of Alice and Bob knowing that they measured the same, even though they did not measure in the same basis, because they just share the basis. They do not share the measurement results, because sharing the measurement results will just give away their key. So even though there's a 50 chance that they got the same key, the same bit when they chose different bases, they're just going to discard it because they cannot be 100% sure. So now we know that someone can be looking into the quantum channel Alice and Bob are using to send qubits, and they cannot copy their qubits because of the non-cloning theorem that we introduced at the beginning of this lecture. But what if an eavesdropper called Eve is able to measure the qubits and then put them back on the channel? So she intercepts one qubit, measures it in some basis, and then puts the qubit back on the channel. So there's no cloning, so there's no theorem violated. So this is completely valid, okay? So in this case, Alice and Bob have a way of noticing the presence of Eve, the eavesdropper. Since measurement collapses the quantum state and Eve does not know what basis Alice used to encode, Eve, again, like Bob in the last case, has 50% chance of choosing the right basis. But even if Eve chooses the wrong basis, at the end, Bob will measure the intended state with 50% chance. So there's a probability that Eve gets away with it and goes unnoticed. So looking at this, like just for one bit, it looks like a high probability that Eve is able to measure the qubits and go unnoticed. But again, the keys that Alice and Bob will send are 100 of bits long. So in some bit where Eve was able to eavesdrop, there's going to be something that tells Alice and Bob that there's an eavesdropper. So let's just do an example. So Alice chooses the rectangular basis, bit 0, and will send 0 and sends it, okay? So now, instead of getting to Bob, Eve will intercept it, and let's say she chooses the diagonal basis, and she gets minus. So she would think Alice intended to send bit 1. And then she sends the exact same state that that she measured back to Bob, and let's say Bob chooses the rectangular basis. But now Bob will get 0 with 50% chance and 1 with 50% chance. So what happens here? When Alice and Bob share their key, share their string of bases, they will see that they chose the same basis, so they're expecting both to get the state 0. But they have a 50-50% chance of doing so. So if they measure 1, they will notice if, because they know something's going on, because they chose the same basis, so they must have the same state. But since they did not have the same state, there must be something going on between Alice and Bob, and that's if. But what happens in this case? They will just get the same. They will get the same bit, and they will not notice B. So in this case, if we go unnoticed, and if she had chose, if she had coding bit 0 here, she will have the key. So yeah, just one thing I didn't say, to notice if Alice and Bob had to share some bits of their final key in addition to the bases they used. So let's just say that Alice and Bob got their final keys. So let's say Alice has 0, 1, 0, 1, 1, and Bob has 0, 0, 0, 1, 1. They're just gonna choose some random bits from there. So there's this one and this one, maybe this is random. So this one and this one. So they're gonna share. Bob will share 0, 1, and Alice will share 1, 1. And since these are not equal, they will know that if was there. Okay. But if they just choose some random bits, so let's just say they chose this one, then the shared key will be 0, 1 in both cases, and they won't notice if, even though she was there, and they could have noticed her if they chose the bits on marked with red. So there's still a chance that they don't notice if. So yeah, let's just look at an example of this. So now we'll first look at an example in which if is able to intercept the qubits sent from Alice to Bob and go unnoticed. So let's just first put the basis from Alice. So this is the rectangular basis, rectangular, diagonal, diagonal, diagonal. So let's just right away discard in the basis in which Alice and Bob did not choose the same. So that's just the third one. Okay. So now let's go through it. Okay. So first qubit, Alice gets 0. If measures on the diagonal basis and gets bit the qubit minus, which corresponds to the bit 1. And then Bob measures in the rectangular basis, but remember that he has a 50 chance, and here he is lucky enough to get the same state that Alice wanted to send. So bit 0, there's no problem here. Again, but now with the second bit, if even chooses the same basis, so there's no problem here. The measurement is done always in the same basis, so the state is not disrupted at any point. The fourth qubit, again, they chose the same basis always, so there's no disruption at any point. And then in the last one, Eve chose the wrong basis because Alice encoded in the diagonal basis, but she gets the 0 qubit, the 0 bit. And then Bob chooses the basis that Alice intended, and is fortunate enough because he again has a 50-50% chance. But again, he has good luck and measures the state Alice wanted to send, so there's no problem. So let's just see. This is 0, 1, 1, 0. This is 1, 1, 0. So the final key that Alice and Bob have, is 0, 1, 1, 0. Okay, and independent of the bits they're gonna share with each other, all the key is the same, so they will not notice if, because it is as if it wasn't present because they got the same final key. But if's key is 1, 1, 1, 0. So even though if was able to go unnoticed Alice and Bob didn't detect her, she doesn't have the right key, so she won't be able to do very much with this key. So the protocol is even safe, even has a degree of safety, sorry, if Alice and Bob do not detect Eve, because Eve may have made some wrong bases, may have chosen some wrong bases, and she will have a random result in that qubit. So now let's look at the more realistic situation, because this was just too much good luck for Eve to go unnoticed. So this is like a more realistic situation in which Eve will be noticed after a few bits. So just let's get the basis for Alice, rectangular, diagonal, diagonal, and we can again eliminate the third qubit because Alice and Bob chose wrong base, okay? And so now let's go qubit by qubit. So in the first one, again, Eve chooses the wrong basis, but Bob chooses the same basis as Alice, but he will have a 50-50% chance because he will receive the minus state. Again, this time he's lucky enough to choose to get to measure 0. Okay, so in the second qubit, they choose, all three of them choose the same basis, so they're safe. In the fourth qubit, it's the same. The three of them choose the same basis. But in the last qubit, Alice sends the plus state, Eve measures on the rectangular basis and gets the 0 state. And again, Bob will choose the same basis as Alice, so they think they need to get the same state. And then, but in this case, since he has a 50-50% chance, 50-50, now instead of the plus state, he gets the minus state. So the final key will be different from Alice and Bob. So final key from Alice will be 0, 1, 1, 0. And Bob will be 0, 1, 1, 1. So now they will choose some bits to share. So if they choose some of these ones, they will not notice that they have a different key, so they will not notice the presence of it. But if they choose this one, they will notice the presence of it because they are supposed to have the same bit on the last qubit because they chose the same diagonal basis. So if they share last bit, they will notice if. But if they share some of the other 3 bits, we are still safe because for beginners, the key is different, so the protocol will not function. The one-time pad or the RCA protocol will not function between Alice and Bob, so they will know something is going on because their keys are not the same. And even if for some think they are able to use different keys for something, Eve has a different key. Eve's key is 1110. So even though they do not notice Eve and the different keys are somehow managed to work, Eve won't have the same key, so she cannot do anything. So that's pretty much it. Are there any questions? But I saw a question and that said, how do they know which basis to discard when they have when they have chosen the wrong basis? So they share that information. They share it classically. They send. So yeah, in this case, Alice chose R, D, 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 and Bob chose R, D, D. So they share this with each other and they can do it on their own. They see that the qubit on the middle, they did not choose the same basis, so they discard that one. This information is publicly shared, and this does not give away any information about the key because the basis does not give away the actual bit, because for the rectangular basis you have 0 or 1, so it can be either 0 or 1, so it can be any of the 2 bits. So you don't give away any information about the actual key, you just give away information about the measurement basis, which is not something safe to do. Any more questions? Okay, so if Alice chooses, for example, diagonal 0, so Alice chooses diagonal 0, which is plus state, and Bob chooses the same thing, does he still have 50% chance of measuring? No, because now Bob will measure on the diagonal basis. So measuring in the diagonal basis, like with the last lecture with Mehil, you can see that measuring the diagonal basis is measuring in the plus minus state. So with certainty, you will get either the plus state or the minus state. And since the qubit is already in the plus state, you have 100% chance of measuring the plus state. And yeah, there's no way that in this case, Bob measures the minus state. But just remember that we are considering an ideal quantum channel, quantum measurements, so that there is no noise. But there's a nice thing about this, that if there is noise, we can just make that the noise is equal to if. So we can just consider if and noise as the same thing. So if there is too much noise, we may think that there is someone eavesdropping, and then we just go again and repeat the protocol if we think there's either too much noise or someone eavesdropping, which we consider to be the same thing. Is there any more question? Any other questions?
So just to clarify, when you mean rectangular and diagonal basis, in this case, you would say like it's the Z basis and the X basis, right?
Yeah, yeah. The rectangular and diagonal basis are just like, because this is usually applied with phonons, but yeah, the rectangular basis is just the computational, which is 0 and 1, and the diagonal is just the Hadamard basis, or it is also called the X basis, which is the plus minus. Yeah. Any other question? Okay, so I think there are no more questions, but again, if some question when doing the problem sets or rewatching the lecture arises, just make sure to send a message to the Q&A channel on the Discord server. We're there to help. We will get to you as soon as possible. And yeah, just remember at 8:30 IST, we will have the talk with the person from Qiskit Cambridge, which will be talking about quantum compilers. This is, it may sound a bit difficult for beginners, but he clarified that this is suitable to beginners and even people from outside the quantum computing community. So don't be afraid, just join and you will have a good time. Okay, thank you guys.
All right. Bye, guys. Hope you enjoyed this one.
Bye, guys. See you.